Hi everyone. This is a lesson about the applications of the derivative, and it is actually going to be called DAPS for Derivative Applications 1, right? So this is our lesson DAPS 1, and it's a really great lesson because it shows us about how a single idea, in this case the derivative, has so many interpretations. And that is what is so cool about mathematics. As Joseph Fourier, a very famous French mathematician, has said, mathematics compares the most diverse phenomena and discovers the secret analogies that unite them. So we've been studying the derivative, and now you understand a lot about what the derivative is and how to find the derivative mathematically, what all of that means. And now you're going to see that that one mathematical idea can be applied to so many different subjects. Mathematics is called the queen of the sciences for this reason, that the ideas in math are so widely applicable that they kind of underlie all of the other sciences. And not only the sciences, but today math is used in I could almost say everything. So in finance or in economics or in predicting even human behavior and sociology and psychology everywhere. This idea of the derivative and other mathematical ideas are so widely applicable in such different fields. So, we are going to start by talking about a few examples of how the derivative can be applied in different fields, what it means in different fields, and we're going to start with our physics example, which you're already familiar with: position, velocity, acceleration, right? So always remembering our IKEA Swatch ladder, which starts with position, S for position, and as you go down this ladder, you take the derivative to get the next equation each time. So if the position of a particle in example 1 is given by the equation f of t is equal to t cubed minus 6t squared plus 9t, and I guess that's it, where t is measured in seconds and s in meters, and we're asked to find the velocity. With the derivative, we now have a powerful tool because we can now write an equation that gives us the velocity at any time, and that equation would be v of t, which you know is simply the derivative of s. So v of t is 3t squared minus 12t plus 9. The units of this s are meters because it's measuring a position. The units of this v equation would be meters per second, right? So we put in seconds for the time. The v that comes out will be in meters per second. What is the velocity at t equals 2 seconds or 4 seconds? Well, we have a velocity equation for any time, so we just have to put in our time and we get out our velocity. So v of 2 would be 3 times 4 minus 12 times 2 plus 9. So that'll be 12 minus 24 plus 9, which is equal to negative 3 meters per second. V of 4, well, we just put 4 into our velocity equation. 3 times 16 minus 12 times 4 plus 9, and that would be 9 meters per second. Okay. When is the particle at rest? At rest means the particle is not moving, and it doesn't have to be at s is equal to 0 to not be moving. It not moving means v will be equal to 0. Okay, so we take the velocity equation and we set it equal to 0 and we solve. This is a quadratic equation. You can factor out a 3 and divide both sides by the 3. Then you have t squared minus 4t plus 3 is equal to 0. T minus 3 times t minus 1 is equal to 0, which means t is equal to 1 or t is equal to 3. At 1 second and 3 seconds, the particle is at rest. And by the way, particle just means whatever is moving. It's an object. And in these type of problems, the position, we're moving along a straight line. So we're either moving backwards and forwards along the x-axis or the y-axis, or the z-axis. We're just moving on a straight line. When is the particle moving forward? That is in the positive direction. Well, particle moving forward means its velocity. Remember, the velocity is the derivative of the position, right? Which means it's the limit as delta t goes to 0 of delta s over delta t. So that means that if the delta s is positive, then the velocity will be positive. That means if the particle is moving in the positive direction, the velocity has to be positive. So we're going to take a look at the velocity equation, which was this quadratic equation. Let me just rewrite it here. We had our velocity equation. We'll just take it like it was to start with. 3t squared minus 12t plus 9. 3t squared minus 12t plus 9. We can divide out the 3, right? Or we can factor it and say this is 3 times t minus 3 times t minus 1, right? That's our factored form of this velocity equation. Actually, I'm just going to say this is the velocity equation here. Okay, so now we need to think about the SIGN, or the sign of our velocity, right? So you might remember this from pre-calc or algebra 2. If you don't, it's not very hard to learn right now. We're looking to find the sign of this quadratic factored equation. So you take the factored form and you find the roots. The roots we already found were at 1 and 3, and you put those on your number line, 1 and 3. And then you're going to check points on in each of these three intervals that the roots divide the line into, right? So we've got 3 intervals, and we just put in different test points here. So for example, for this interval right here, we can put in t is equal to 0, just check the velocity at that number, v is equal to 0, and we would get, you can take any point in this interval, right? So I picked 0 because it's a convenient number, and v of 0 is equal to 9. So 9 is positive, so therefore the velocity for this whole time here is going to be positive, right? And I'll talk about why in just a minute, but for the yellow interval, I might pick 2 as a number to check there, right? So I would go v of 2, and I would come out with, you can use the factored form and get 3 times 2 minus 3 times 2 minus 1, which would be 3 times negative 1 or negative 3. So the velocity is going to be negative for this whole time. And then you can put in, maybe v of 4 here and find that that's 3 times 4 minus 3 times 4 minus 1. And so that's going to be positive 9. So it's positive again over here, right? Okay, and if you're wondering how can we be sure by just checking one point in each of these intervals that the particle is actually, that if you just check one point, how can we be sure about the whole interval? Well, the reason is that the velocity is continuous, right? You can see that both from the equation, which is a polynomial, as well as from the fact that it's a physical quantity, so it's going to be continuous. Well, once the velocity is continuous, we can say that by the IVT, right, v of t basically cannot change sign unless it passes through 0. So if you remember this from Unit 1, this is the idea that, if the velocity, in order to go from, if you're just thinking of a velocity graph, right, for the velocity to go from negative to positive, it has to cross through 0. And we know that the only two places where it crosses through 0 are here, v is equal to 0 at time 1 and v is equal to 0 at time 3. And so those are the only places where it could change sign, and that's how we can make this sign chart. So back to the question here, we can say that the particle is moving forward for the time 0 is less than t is less than 1, and for t is greater than 3, not 0, t is greater than 3, And this is because you need to justify your answer by saying it's because v of t is greater than 0 or positive in those intervals. Okay, to find the total distance traveled by a particle, we need to separate it into the times when, so we're looking here for the first 5 seconds. So we know that if we look at t is equal to 0 to 1, then the velocity is greater than 0. 1 to 3, velocity is less than 0. 3 to 5, velocity is greater than 0. So particle is moving forward and then backward and then forward. So what we're going to do to find the distance is we're going to find the distance traveled in each of these intervals, 0 to 1. And for that, we just have to do s of 1 minus s of 0. And then we'll do s of 3 minus s of 1. And then we'll take absolute values so that if you're moving backward, we want to add up all the distances. So we'll do s of 1 minus s of 0, s of 3 minus s of 1, and we'll do s of 5 minus s of 3, right? And the idea is that the particle is, moving forward and then backward and then forward. If we want to add up all these distances, it's like we're adding here s of 1 minus s of 0, and then it turns around, right, and moves backwards, and then at 3, it's over here, so we do s of 3 minus s of 1, and then it moves forward again, and so we do s of 5 minus s of 3. But we want to add everything up, and that's why we need to take absolute values. So if you do this out, it's a matter of taking your s equation, which was up there, t cubed minus 6t squared plus 9t. So let me write that down. S is equal to t cubed minus 6t squared. Is it minus or plus? Plus 9t. Okay, so then, I might just organize, I don't need the parentheses, 9t. So I would just organize my work and find s of 0, that's 0. S of 1, that's going to be 1 minus 6 plus 9, which is 4. And then s of 3, which is going to be 27 minus 6 times 9 plus 27, which is going to be 0. And then s of 5, which is going to be 125 minus, I guess, 150. 25 times 6 plus 9 times 5, 45. So I think that's going to be negative 25 plus 45, positive 20. So I can now just come in here and calculate these. S of 1 minus s of 0 is 4. And that's positive, so I don't need to change the sign. S of 3 minus s of 1 is also 4, but it's negative 4. But I'll take an absolute value to make it positive 4. And then s of 5 minus s of 3 is 20. So I'll add these up and say 28 meters is the distance traveled by the particle during the first 5 seconds. 28 meters traveled from t is equal to 0 to t is equal to 5. Okay, let's move on to find the acceleration. So that's another rung down the ladder, right? So a of t is going to be now the derivative of the velocity equation, which is 3t squared minus 12t plus 9. So it will end up being 6t minus 12 is my acceleration, and a of 4 is going to be 6 times 4 minus 12. That's just 24 minus 12, or 12. Now the units of this are going to be in meters per second squared, because acceleration is another derivative, right? So it's going to be a ratio of delta v over delta t, and then of course it's an instantaneous rate, but delta v is a change in velocity that's already in meters per second, and we're dividing by another seconds, so it becomes meters per seconds times 1 over seconds, or meters per second squared. Okay, slowing down. Mathematical tools, because coming back to the beginning, mathematics compares the most diverse phenomena and discovers the secret analogies that unite them. Have a wonderful rest of your day. Okay, graphing the position, velocity, and acceleration. Well, you often will have a calculator for RLM problem. RLM stands, by the way, for rectilinear motion, like this, which is particle moving in a straight line. But if you don't have a calculator, that's okay too. We can use our pre-calc skills to think about how the equation might look. So the S was, let's see, I lost my S equation. S was t cubed minus 6t squared plus 9t. And then V was, it was therefore 3t squared minus 12t plus 9. And then A was 6t minus 12. Okay, so S, I wouldn't necessarily expect you to know how to plot, but V and A we can certainly plot without a calculator. So for A, it's going to be a line of intercept negative 12 and slope 6, right? So that's going to look something like this. It's going to have a rise over run of 6 units. This is not to scale, right? So negative, so here I have 6 units down and, 12 units down and 2 over. So this line has a slope of 6. And that would be my acceleration. It would be a linear graph. This velocity equation will be a quadratic, right? And we know that the C value is 9, so I'd be somewhere here at 9. This is not at all to scale. And we figured out that the velocity graph has zeros at 1 and at 3, so it's going to do something like this maybe, and that would be a velocity graph. It turns out that the position graph, being a cubic, it's going to, you could actually figure it out just from looking at these, right? Because the velocity is the derivative of the position. So the position must be increasing for this first stretch here. I really shouldn't extend these graphs for x less than 0, because t less than 0, because time is never negative. But the position graph, it's going to be increasing until 1, and then it's going to be decreasing, and then it's going to be increasing again after 4. So it turns out that the position, and that also matches up with what we said about the moving forward and moving backward, right? Because here we are, when the velocity is positive, the position is moving forward, the position is increasing. When the velocity turns negative, then the position starts to move backward. Like, we're still positive, but the position number, if you think of it along the x-axis, right, it's decreasing. And then finally, when we get past 3 here, then the position starts to increase again, right? And that's exactly what we decided before. We're moving here forward and here backward and here forward again. Okay, so we need to know how to look at those graphs, how to make them with the calculator, which is the topic of another video, and how to interpret them. When is the particle speeding up and slowing down? Well, so you have to think about speeding up and slowing down both in terms of velocity and acceleration, right? So if velocity is positive and acceleration is positive also, the particle will be speeding up. That's what we usually do on the highway, right? We're going forward and we're pressing the accelerator. So velocity is positive, and acceleration being positive really means velocity is increasing, and so we are speeding up. If the velocity is negative, so you're moving backward, right? If your acceleration is also negative, then your velocity is going to become a bigger and bigger negative number, and that is also going to be speeding up, okay? Now, if the velocity is positive, that is, you're going forward, and the acceleration is negative, this is when you're braking on the highway and you're going to be slowing down, right? If the velocity is negative, so you're going backward, but the acceleration is positive, that's going to be slowing down in the backward direction, right? So you know that acceleration happens because of a force. So you can think about it as if the force is in the same direction as the velocity, or the same sign as the velocity, then the particle is going to be speeding up. And if the force is in the opposite sign as the velocity, then the particle is going to be slowing down. So mathematically, we're just going to look at our sign chart for the velocity, and that came out to be like this, right? And we're going to compare that to a sign chart for the acceleration. So the acceleration was 6t minus 12. So that one, this was 3 on the velocity. So on the acceleration, this has a 0 at t is equal to 2, right? And we do the exact same thing. The acceleration is positive on the right side of that 2. You can test a point, put in 3, and then you get 6 times 3, 18 minus 12, which is 6, that's positive. If you put in 1, you get 6 minus 12, which is negative, right? So what we're finding is that you can now compare the signs of the two quantities, right? So we'll have to actually draw this a little bit better. So if I put 1 and 3 on my acceleration chart and my velocity chart, you'll see it better. For this first stretch between 0 and 1, right? So I'm negative, negative, positive, positive on the acceleration. Okay, so for the first stretch between 0 and 1, this is positive and this is negative, so we're slowing down. Then from 1 to 2, velocity is negative and acceleration is also negative, so we're speeding up. Then from 2 to 3, velocity is negative and acceleration is positive, so we're slowing again. And then in the end, we start to speed up again, right? So we're speeding up. I would put the answer here maybe. So speeding, wrong color, sorry. So we're speeding up, wrong color again. Speeding from t is equal to 1 to 2 and t is greater than 3. And the reason is velocity is positive and acceleration, well, I guess we should say them separately because we can't say them together. So we could say it this way. 1 to 2 because velocity is negative and acceleration is negative, and t greater than 3 because velocity is positive and acceleration is also positive, right? And then slowing is going to be from 0 to 1, and 2 to 3. And those are going to be because velocity is, let's see over here, positive here, and acceleration negative. And over here, velocity is negative and acceleration is positive. Okay, so that's how we check for speeding up and slowing down. Okay, our next example is very similar, but the math is going to the physics is similar, the ideas are similar, physical ideas, but the math is going to look different because the position equation, instead of being a polynomial, is this: f of t or s of t is equal to t squared e to the negative t. That's the position for t greater than 0. And s is equal to f. I don't know why they do this sometimes. Why didn't they just call it s of t? Anyway, where t is in seconds and s is in feet, right? So position is in feet, time is in seconds, velocity will be in feet per second, okay? So first we're going to find the velocity by just differentiating that position equation. So first times the derivative of the second plus the second times the derivative of the first. Now, if you're wondering about e to the negative t and its derivative, just remember in is negative t, out is e to the t or e to the x, in prime is negative 1, out prime is e to the t, right? So if I make my out prime of in times in prime, I get e to the negative t times negative 1, which I can write as negative e to the negative t. So that's how I'm getting this negative sign and this right here, okay? Okay, so that's my velocity. If I want the velocity at any time, I just put in the time. So v of 1 is equal to negative 1 squared e to the negative 1 plus 2 times 1 e to the negative 1. That's negative 1 over e plus 2 over e, which is 1 over e, and this is in feet per second. Find all times when the particle is at rest. At rest means velocity is equal to 0. So I'll take my velocity equation and try to figure out when it's equal to 0. Negative t squared e to the negative t plus 2t e to the negative t, set it equal to 0. Factor out a t and an e to the negative t, and then in parentheses we have negative t plus 2, right? And then we'll set each factor independently equal to 0 and solve. So t is equal to 0 will be one time when we're at rest. E to the t is never equal to 0, because if you remember, the e to the negative t graph looks like this, right? And it never hits its asymptote. So it's never 0. And then negative 2 plus t equals 0 gives us one time at t is equal to 2. So we're at rest at t is equal to 2 and at t is equal to 0. When is the particle moving in the positive and the negative direction? So again, we have a velocity function which is continuous, and we can then just make our sign chart, and by the IVT, really, though we never have to say that in a problem like this, we just put the 0 and the 2, those are the times when we're at rest. We put that on our sign chart, and then we check for signs, points in between. So I might do v of 1, which is between 0 and 2, and I'll get negative, well, we did v of 1 already, right? And we got 1 over e, which is positive. So that means I'm positive for this whole time. And then I'll do v of maybe 3, and that's going to be, I think, also positive, but let's double check. V of 3, I like to use the factored form when I do this. So I would have 3 times e to the negative 3 times negative 3 plus 2. Oh, I'm sorry, it's negative. It's going to be negative 3 over e cubed, right? So the velocity is negative for v is equal to 3. And so that means we must be negative starting at 2. So the particle changed direction at t is equal to 2, right? So we would say that we are moving in the positive direction here. Let me say it over here. So we're moving, they asked for both. So positive direction, or when are we moving forward, right, or upward? That would be from 0 to 2, because v is greater than 0. And then we'd be moving in the negative direction for t greater than 2. And that's because v is less than 0 on that stretch, okay? Okay, the next question says the total distance. So we have to break our motion up into forward and backward, right? We have both, or moving positively and negatively. So from 0 to 2, we're going forward, and then from 2 to 6, because we're asked for the first 6 seconds, we're going backward. So we're going to do s of 2 minus s of 0 and do an absolute value, and then we'll do s of 6 minus s of 2 and do another absolute value. So s of 2 minus s of 0, I believe, comes out to be 4 over e squared minus 0, which is 4 over e squared. And then s of 6 minus s of 2, I guess, comes out to be 36 over e to the 6 minus 4 over e squared, okay? And we're going to have to take an absolute value of that. Okay, so if you had no calculator, you would just leave your total distance answer as 4 over e squared, and I would just leave it as this absolute value of 36 e to the 6 minus 4 over e squared, right? That's a no calculator answer. If you put this into the calculator, you're going to come out with an answer of 0.9934. We'll keep all of our answers to 4 decimal places, so 0.9934 feet. Okay, find the acceleration of the particle at time t and at t is equal to 1. So now we have to take that velocity equation and differentiate it one more time. So the velocity equation had come out to be negative t squared e to the negative t plus 2t e to the negative t. So you can see we're going to have to do product rule a couple of times. And we're going to end up here with a longer equation. So product rule on this first piece will give me the first times the derivative of e to the negative t is going to be negative e to the negative t. So I can make this positive out front, right? Plus the second times the derivative of negative t squared, which is negative 2t. So then this positive becomes a negative here. Okay, and then over here, 2t to the negative t, so negative 2t to the negative t plus 2e to the negative t, okay? So that's going to be my acceleration equation. And you can combine these two terms here. So t squared e to the negative t minus 4t e to the negative t plus 2 e to the negative t. And you can pull out an e to the negative t if you like from there. And to find acceleration at 1, you just put 1 into everything, and you would get 1 times e to the negative 1 plus or minus 4 e to the negative 1 plus 2 e to the negative 1, which all boils down to, I guess, negative e to the negative 1 or negative 1 over e. And in a calculator, that's about negative 0.3678 feet per second squared. Incredible. Okay, graphing the position, velocity, and acceleration equations, that's a great calculator exercise that you should practice doing. Actually, maybe I'll show you how to do that. Okay, so here's my calculator, and I'm gonna go into my function editor, clear out whatever there is in there, and I'll put in my three equations for position, velocity, and acceleration under y1, y2, and y3. So first of all, into y1, I'm gonna put that's y2, so I want to be in y1. I mean, it doesn't really matter, but I'm going to go for y1 and say x, and then I'm using my hat squared, arrow over, come down out of the exponent, and then second division gives me my e. There's also another way to do that, which is second ln, and then e to the, what do I want? Negative t, right? So e to the negative, make sure you use the negative sign at the bottom of your calculator when you're writing your equations like this, and then negative x. Okay, so this is my position. Now, something cool in the calculator is that you can actually, we took the derivative here, right, by, doing it manually, but you can also make the calculator for the purposes of the graph. It's not going to give you an equation for the velocity, but you can actually do the derivative here through the calculator, and that's, of course, using math 8. So math 8, numerical derivative or n derivative, you hit enter, and you get the derivative template right here. And so we can now put in x over here, use the x next to the green key, and then here you want to put in y1 because we're taking the derivative of y1, and to do that you go alpha trace, green button trace, and then put in the function you want. I want y1, so I'll just hit enter there, and then x equals x. Okay, so now y2 is the derivative of y1, and I'll do that again to make y3 the derivative of y2. So then d dx, and then x, and then now I want alpha trace y2, and x equals x. Okay, so now if I graph, I should, oh, my window is a little strange, so let me go ahead and change the window. So here's my window. I'm going to make it negative 10 to 10. Actually, I don't need to make it negative 10 to 10, right? Because this is a time problem, so it starts at 0, so I could just put in maybe -1, and then let's go until, yeah, 10 seconds, and then the y can be -10 to 10 for now, and we might change that later. So here's my graph. That's the position, and then there comes the velocity, and I'm already seeing that I want to change the scale on the y. So to stop the graph, you just hold the on button down for a while, right? So I'll just do that to cancel the graph, and I don't need all that y clearly. So I'm going to make it like 2 for my y, maybe -2 to 2, and see what that looks like. That looks a little better. You can see the graph more. I don't even need 2. I could have done 1. But there we have it. There's our position, our velocity, and see how, by the way, it changed at 2, which is what we predicted, and it never comes back above into the positive side, right? And then we've got acceleration, which should be coming in anytime now. There it comes, okay, and the acceleration is right here, changes sign right there, and then not sure if it's going to change sign again. It does. It actually does, I think. So we'll probably change the window on this again so we can see things a little more clearly in a minute. Okay, the graph can be a little slow, that's for sure. It's still finishing up, right? So here I could have cut down my window on the right. I don't really need all the way to 10. I could just do it to 6. I think the second part asked us to 6. So yeah, I could just do that. And then I also can reduce my y from -1 to 1. And I think that will give us a better looking graph. The second time it plots going to be faster than the first time because it's already calculated the points. So it should go a little bit faster here. Okay, there's my velocity. And it is kind of slow still, but hey, just gotta wait. And here's the acceleration now. Okay, so while it's plotting, let's just realize that for the last part here, I think it's asking us, if I'm not mistaken, about speeding up and slowing down. So we already know just from algebra that that is exactly 2 right there. And then we need to figure out this place where the acceleration changes sign, and I think one more place where the acceleration changes sign. And then based on that, we'll be able to say when we are speeding up and when we are slowing down. So let's do that. And the way we do that is by doing second trace, and you use your 0, number 2, and then you go to the graph you want, which in this case is the black graph. And I'm going to go to the left of my 0 that I'm after, which in this I'm looking for the 0 first. So I'll just scoot to the left of it, give it a left bound, enter, and then scoot to the right of it, give it a right bound, enter, and then a guess, just come close to the 0, hit enter. And so I've found that my 0 is at 0.5857 seconds. Okay, so we'll write that down in a minute. 0.5857. In fact, I better write it down before I forget that. So by the way, it didn't say that in this example, but this should say, when is the particle speeding up and slowing down on the interval from 0 to 6. So we know that acceleration, now I'm just going to write it here, and then I'll have to shut down my calculator screen, and we'll write out the answer properly. But 5857 is one of the zeros on the acceleration. And then if I do the other 0, you got to scoot close to, first you have to be on the right graph, and then you have to go really close. Well, you don't really, but it'll be faster if you go close to the second 0, hit enter for the left bound, Scoot over to the right of that, hit enter for the right bound, and then hit a third enter, and you should get your 0, which is at 3.414. Sounds like pi, 3.414. No, that's 3.14, 3.4142 seconds. Okay, so those are our 2 times when the acceleration hits 0. Okay, so the graph here is basically here. We did this little demo with the calculator, but that's what you need to be able to either, I mean, this would be a calculator problem, so you'd be graphing it with the calculator. I'll just put this over here. And now in terms of speeding up and slowing down, I know that on the position and, well, on the velocity, I'm changing at 2. So from 0 to 2, I was positive, and then I became negative. And then on the acceleration, so this is V, and then on A, at 0.5857, until then I was positive, and then after that all the way until 3.4142 I was negative, and then I became positive again, right? So I'd be speeding up. I'm not going to write out the answer, but you would just write out that you're speeding up from 0 to 0.5857. You're slowing down from 0.5857 until 2. Then you're speeding up again from 2 to 3.4142, and you're slowing down again after 3.4142 until 6, right? So speeding up in the blue regions and slowing down in the red regions. Okay, let's take a look here at example 3. So here we have a projectile shot vertically up from a point 2 meters above the ground with initial velocity 24.5. The height in meters of the projectile, which is basically projectile, just a fancy word for anything that's being thrown, at time t seconds is given by h of t is 2 plus 24.5 t minus 4.9 t squared. So first thing I want you to realize is that you could have done this problem in algebra 2, because this is nothing other than a quadratic equation. It's not written in standard form right now, right? This is not standard form, but you just can write it in standard form, and it looks very much like things you did in algebra 2 when you did projectile motion. So you could do the whole problem with algebra 2, but we want to just show that the calculus does the same thing. And while you can do this one without calculus, if it were not a quadratic equation, like in the last problem, right, then of course you need calculus. Anyway, it says find the velocity of the projectile at time t equals 2 and t equals 4. So there we're just taking h prime, right? V of t would be equal to h prime of t, and that comes out to be, in this case, negative 9.8 times t plus 24.5. Negative 9.8t plus 24.5, and that will be in meters per second. And if you want the velocity at time 2, well, then it's just going to be, put in 2 into the velocity equation, and you're going to get negative 9.8 times 2 plus 24.5, which comes out to be 4.9 meters per second. And then if you wanted V of 4, just put in 4, and you get negative 9.8 times 4 plus 24.5, which is negative 14.74 meters per second. Okay, so we're moving upwards at t equals 2, and moving downwards at t is equal to 4. Okay, when does the projectile reach its maximum height? We know that that would be from algebra 2. You're just finding negative b over 2a for the parabola, right? But here, to find the maximum height, we know that the velocity has to change from positive to negative, right? At the time when we reach our maximum height, we're going up and then we're going down, right? And that cannot happen by the IVT unless we get to the top where the velocity is just for a brief instant, it's equal to 0. So we can take our velocity equation, set it equal to 0, and solve, right? This is like, when is the velocity changing direction? When is the particle at rest, right? Really, that's the same question here. And we get that t is equal to 2.5 seconds when that happens, okay? What is the maximum height? Well, we take that 2.5 seconds and put it into the h equation. So we're just going to do h of 2.5. And so that is negative 4.9 times 2.5 squared plus 24.5 times 2.5 plus 2. And this comes out to be 32.625 meters, okay? When does the projectile hit the ground? Well, the projectile hits the ground when the height is equal to 0, right? It starts off on the ground, I believe. No, it's actually starting off at 2 meters above the ground. So the parabola really looks more like starting at 2, and then it goes up and comes down. We just have figured out that this is happening at 2.5 seconds, that it gets to the top. And we've also figured out that the top is 32.625 meters, right? And now we want to find this, which is the x-intercept of the parabola, right? So we know this, this is actually not calculus at this point, because all we're doing is finding the x-intercept of a parabola. So we just do this, set the parabola to 0, and solve it using the quadratic formula, negative b plus or minus the square root of b squared minus 4ac, which becomes plus 4 times 4.9 times 2 all over 2 times negative 4.9. Please practice putting all of this into your calculator and getting out the two answers, negative 0.0803 seconds and 5.0803 seconds. This is not correct because time can never be negative, and this is therefore the time when we hit the ground. Okay, many. Okay, the last question on that problem is, what is the velocity of the particle when we hit the ground? So for that, we know the time now. So we just put that time into the velocity equation. So I can say it's v of 5.0803, which is negative 9.8 times 5.0803 plus 24.5. And I'm going to come out with an answer of negative 25.2873 meters per second. It's negative because when you hit the ground, the projectile is obviously going downward. Okay, so now that we're all physicsed out, let's switch gears and see how the derivative applies in economics, right? Because remember, the big picture here is that the derivative has different applications in all kinds of fields. The same idea is interpreted differently and is useful in all these different fields. Okay, so economics, we can say that suppose a company has estimated that the cost in dollars of producing X items of whatever widgets they're producing is C of X is equal to that equation there. C of X is equal to 10,000. No, sorry, that's a different equation. C of X is equal to this thing right here, right? And they're saying find and interpret the meaning of C prime of 100, right? So first of all, finding C prime of 100, well, that's not very difficult. We just find C prime of X, which is the constant goes away, and then we have 25 minus 0.909 times 2 would be 0.18x plus 0.0012x squared, right? So that is C prime of x. And then C prime of 100 would mean we're going to put 100 in here for everything. And we'd get 25 minus 18, because 0.8 times 100 is 18. And then here 100 squared is 10,000, right? 4 zeros, which will take away these 4 decimal places. And so I'm going to end up with C prime of 100 is equal to 25 minus 18, which is 7 plus 12, or 19, right? So C prime of 100 is 19. So what does this mean? Well, it means you have to kind of picture this graph and realize that we have cost here and the number of items here, and our cost versus the number of items is this polynomial function. The reason is that, depending on how many of something you're making, the costs are going to be different. Usually when you make a lot of something, it's going to cost you less per item than if you're making just a few of it, right? So we're saying that whatever this curve happens to look like, when we're at 100, the slope of this curve, right? It's a curve, so we're talking about the slope of the tangent line. The slope of the curve at 100 is 19, right? So this curve, this y-axis is in dollars and this x-axis is in number of items. So this slope is really in a unit of dollars per item, right? And so it's really, the meaning is that when 100 items are being produced, the cost of producing one more item would be $19, right? That's called the marginal cost in economics, right? And that is what it means. So if we want to write the meaning, I'll just say when 100 items are being produced, not 1,000, when 100 items are being produced, the cost of producing one more item would be $19. Okay, then it says compare C prime of 100 with the cost of producing the 101st item, right? So this means we can also figure out the cost of producing the 101st item by doing C of 101 minus C of 100, right? And if you do that, you're going to get an answer of, you just put the two C's in, two numbers, 101. Well, we could just do it. So we're really doing here back to our C equation. Actually, sorry, we're not going to do it because we got to go back into the C equation and put in 101 and put in 100. So I'll just tell you the answers. It's going to come out to 2358.0304 minus 2339.0000. And so this is going to come out to 19.0304, right? So the actual cost of producing the 101st item according to this model is $19.03, right? But from our derivative, we could already know that the cost of producing that extra item would be about $19. Now, the reason why it's not exact is because the costs are actually going up in discrete amounts, right? So it's like every next item, while the curve that we're using is a continuous curve that we are using it to model this discrete situation, but we can see that the two come out to be pretty close. Anyway, this is called a marginal cost, and that's what the derivative means on a cost curve. The marginal cost means how much does it cost to produce that one extra item when you're already producing a certain number of items. Okay, we're at our last example, which is a biology example. Consider a population of bacteria in a homogeneous nutrient medium. Suppose that sampling the population at certain intervals, it is determined that the population doubles every hour. In general, this population function is given by P of t is equal to P0 times 2 to the t. What is the rate of growth of the population at t is equal to 4 hours, right? So first of all, let's understand this population equation. We start with a certain number, P of 0 is equal to P0. So we're starting at P0. P0 is some number, like, 1,000 or 1,000,000 or some amount of bacteria. We start at that number. This is a number, or we can even say it's the initial number of bacteria. And then we're saying that basically 1 hour later, we're going to have 2p0, right? And then 2 hours later, we're going to be up at 4p0, right? And so on. And so this is the curve, right? That it's an exponential curve. It's 2 to the power t. That is the multiplier. So when we are talking about the rate of growth, then we know that we'd be talking about dp dt on this curve, right? The slope of the tangent line at any particular place on this curve would be the rate at which the bacteria are growing at that particular instant. And you can see that this curve is getting steeper and steeper as time goes on, right? So bacteria are going to be growing more slowly at the beginning and faster as you go high as the time gets more and more, which makes sense because there's more and more bacteria and they're all doubling every hour. So dp dt, we know from the derivative of 2 to the x, right, is equal to 2 to the x ln 2. So we're going to use that here to get dp dt is p0 is just a constant, 2 to the t ln 2, and I'll put it out here as p0 ln 2, 2 to the t, right? This whole thing is a number here, okay? So you see that we can find the rate of growth for these bacteria, and in this biology example, that's very useful to know the rate of growth of the bacteria. If we wanted to know the rate of growth of the bacteria at t is equal to 4, which was the question, then I just have to do dp dt at t is equal to 4 is equal to p0. They didn't tell us an initial number, so I'll leave it at p0 ln 2, right, times 2 to the 4, right? Just putting it. So it'll be 16 ln 2 times p0, right? So, I mean, if p0 was 1,000 bacteria, then at t is equal to 4, then the rate would be, the rate of growth would be 16,000 times ln 2, which is also a number, by the way. So if I go in my calculator and I do 16,000 times ln 2, I would get 11090.3548, and this is in bacteria per hour, right? That would be the rate of growth of the bacteria at t is equal to 4 using this model. Okay, so I hope that I've convinced you that the derivative is widely applicable to all kinds of subjects, and that the meaning of the derivative, right, is going to depend on the context that you're in. So in physics, the derivative is used for really just an incredible number of other quantities that are important in physics. You saw velocity, acceleration in the examples that I gave you here, but also things like density or electric current, right? I'm just giving you some more examples, or power or temperature gradient. All of these are things that are important to physicists, and they're all measured by the derivative. Chemists are going to use derivatives as well to measure things like the rate of reaction, or the compressibility of a gas, or various other quantities. Biologists, you saw just now, right, an example of population growth, right, or even things like blood flow, the rate of blood flow in your body, or other things. So many other things would be measured using the derivative. In economics, you just saw an example of marginal cost, which means you make one more item. You're already producing a certain number. You're going to make one more. How much is it going to cost you? That's a derivative. Marginal profit, by making that extra item, now how much more profit are you going to make? That's another derivative. And even in things like sociology, when you're looking at something like the rate of spread of a rumor, right? That is something you're gonna try to model and estimate using a derivative. When we have the pandemic, for example, back here, we could say under biology, the rate of spread of a virus. That's definitely a derivative idea, right? So, anyway, the derivative, back to the beginning, is an incredible tool, absolutely changed the world, and it's just